Welcome back for our last video on the polar coordinate system. We're going to be taking a look at how to graph conic sections that are written in the polar coordinate system. We'll find that we need the same pieces of information that we did in the rectangular system. We'll need to know where the center is, where the focus points are, where the directrices are, and where the vertices are. But in this case, we're going to be starting with the equation in polar coordinates, which means that the pieces of information we'll have at the beginning are quite different than what we saw in the rectangular system. So let's get started and take a look. Let me share my screen with you so that you can see what I'm seeing. Now, what we want to look at are the equations. Now, we do things a little bit differently in the polar coordinate system for conic sections. And primarily, again, we are talking about the parabola, the ellipse, and the hyperbola. So yes, a circle is also a conic section, and so is a line, and so is a point. But we're mostly concerned with the ellipses, the hyperbolas, and the parabolas. We're going to assume that in the polar coordinate system that we've located one of the focus points, or the only focus point for a parabola, at the pole, in other words, at the origin. Now, this is different from what we typically see in the rectangular system, where the nicest of them are centered at the origin. That center is at the origin. But in the polar coordinate system, it makes more sense to have a focus point at the pole. And the reason for this is because in the real world, when you talk about the focus point, for example, the sun is at the focus point of the elliptical path that the planets take around the sun. So anything moving in a gravitational field is moving in an elliptical pattern with the source of the gravitational field located at one of the foci. So it makes sense to put that location at the pole or at the origin. If you have a comet that is approaching the Earth and it also approaches cyclically, then it's also on an elliptical pattern, but this time with the Earth at the focus point. If we have a comet that comes close to Earth but never comes back again, then it's following a hyperbolic path. And again, the Earth is at one of the focus points, exerting a gravitational field which is warping the path of the comet close to Earth. So this is going to be a little bit different than what we saw in the rectangular system. When we're looking at these equations, we see that the equations are very, very different. When you're looking at the equation of a conic section in the polar coordinate system, you get this equation R equals E times the focal parameter distance divided by 1 plus or minus, it'll be one or the other, not both, the E cosine of theta. Now, E represents eccentricity. It's very difficult to get that special stylized E inside the equations. So it looks like E, like Euler's number, but it's not. It's the eccentricity. So we have the eccentricity times the distance between a focus point and the directrix. That means that what we have in these equations, which describe conic sections, we have the eccentricity and the focal parameter. We do not have A, the distance from the center to a major vertice, and we do not have B, the distance from the center to a covertice or a minor vertice. We don't have that. What we have instead is the actual eccentricity, which would be between open 0 and open 1 for an ellipse, and greater than 1 for a hyperbola, and equal to 1 for a parabola. Notice that these equations are very similar. Notice that they both start with the constant positive 1 in the denominator. That's going to be a critical part to making sure that your equations are in working form. This must be a positive 1. If it's negative, you're going to have to multiply numerator and denominator by a negative 1, which of course is just 1. If it's 2, then you're going to have to divide numerator and denominator by 2, because 1 over 2 divided by 1 over 2 is still 1. But that will make that leading constant in the denominator a 1. Then we have either cosine or we have sine being multiplied by the eccentricity. Now remember that eccentricity is always non-negative. It's 0 for a circle, but otherwise it's strictly positive. So we're going to have here basically that the eccentricity is going to be multiplied by a trig function. Now the sign that's in between is going to determine the relative location of the directrix line that's closest to that focus point located at the pole. We're going to have to look at the sign of the focal parameter compared to the sign in the middle. If the signs are both positive, then it will be in a positive direction related to the trig function. Cosine is x, so it controls left and right. So it would be either to the right of the pole if the combination of these signs was positive, or to the left of the pole if the combination of these signs is negative. Now that supposes you're already in working form with a positive 1 here. If, however, you have sine in the equation, sine is y, so it controls the vertical. That means that your directrix line closest to the focus at the pole is either going to be above the pole running horizontally or below the pole running horizontally. So again, it's the combination of signs between the focal parameter and the sign in the middle in the denominator. If it's positive, the directrix is above the pole. If it is negative, it is below the pole. Remember that the eccentricity is always, in this case, strictly positive, because this is not how we write the equation of a circle in the polar coordinate system. It's just r equal a constant. That's a circle. And you'd notice that here, basically, it would all drop out if the eccentricity was 0, because we have 0 divided by 1, which would be 0. So that, of course, is a single dot. But I guess you could call it a circle, a degenerate circle. So we're mostly concerned with the sign of the focal parameter in comparison to the sign in between the terms in the denominator. So these are the two equations that we have. And when we're looking at this, we can now determine how to find it in working form. So what we want to do is I'm going to start with an example, 12 divided by -2 plus 6 cosine of theta, and we want to put it in working form. So I'm going to go through the steps that I use in order to get these polar conic sections into working form. Remember, working form must have a positive 1 in the denominator as the first term. So the first thing to notice is we want to make that constant term in the denominator a positive 1. If it's not a positive 1, then you need to multiply by the reciprocal of it divided by itself. So for example, if it's a -2, you need to multiply by 1 over -2 times 1 over -2. We need to get rid of that -2 and make it a positive 1. So you'll see here I multiplied by the reciprocal, 1 over -2 divided by itself, 1 over -2. This makes it just 1, so I'm not changing it, I'm changing the way it looks. So 12 divided by -2 is -6. -2 divided by -2 gives me the positive 1 I was after. 6 divided by -2 gives me a -3. So now I have -6 divided by 1 minus 3 cosine of theta. And now I can actually tell a little bit more about the function and what I have. Once I have it in this form, I want to look at the absolute value of the coefficient of the trig function. So I look at the second term in the denominator, second. So when I'm looking at -3 cosine of theta, I know that that has to be the eccentricity times the trig function. But eccentricity here is strictly positive. So the eccentricity is 3, not -3. It is 3. Because that's larger than 1, I know that this graph's a hyperbola. All right, so I already can tell that this is graphing a hyperbola. All right, and those are, of course, the values that we see here. Again, the eccentricity is the absolute value of that constant. It does not include the sign. All right, so once I know that it is a hyperbola, I want to think about the focal parameter, the distance between the focus and the directrix line. So in that case, I know from the formula that we had up above, which is right here, that once I get this 1 in the denominator, the numerator becomes eccentricity times the focal parameter distance. So the numerator becomes this eccentricity times d. So I want to find that value. So I've got eccentricity times d. So I've got E times d equal to -6. So let's go ahead and write that down. So we have the eccentricity, which I write as a cursive E, which is not how I write Euler's number, equals -6. But I also know that the eccentricity from what I found in the second step is 3, always strictly positive. So this gives me 3 times d equal -6. So I know that d is equal to -2. Now, the distance is 2. But the sign is going to help me locate that directrix line in relation to the focus point at the pole. So the next step is to take the sign of the focal parameter, the distance from the focus to the directrix line, and compare it to the sign in the denominator. Now this is a negative and that's a negative, and the negative in the numerator is coming from the focal parameter. So I've got 2 negatives, and 2 negatives multiply together to make a positive. Because it's positive, it's going to be located in the positive direction. If it's sine, it will be above. If it's cosine, it will be to the right. In our particular equation, it was cosine, so we know the directrix line is going to be to the right. Now, when we're looking at this, since it's going to be to the right, that means that basically what I have, if I imagine my graph, is I've got a focal point here at the pole at the origin. Maybe I should make that a different color. There's my focus point. And then over here somewhere, let's add a pen and make it, oh, gray. Over here somewhere to the right, I have a directrix line. Right? So again, because it's cosine, it's going to be running this way. Now, a cosine is going to open left and right. So somewhere I've got to have another focal point and another directrix. Right? Remember that a hyperbola has 2 foci, 2 directrices. But I know at least half of it is going to fit in here like that. So at least half of it is coming in somewhere, somehow, some distance like that. And then I just have to locate the other one. Well, now the thing is that the 2 directrices are between the major vertices. Now I know that this one has to go this way because the focus point is inside the hug of the arm. So I know it has to open to the left. That means the other part of it has to be over here somewhere, opening out to the right, which must mean that somewhere over here is another directrix line, and there has to be another focus point over here, right? So because I've eliminated, or because I've determined that the directrix line is to the right, I know that most of the hyperbola is in fact to the right, right? Now, if the product of the sign in the numerator and the sign in the middle of the denominator is negative, then it would have been in the negative direction. I would still have had a focus here, but the directrix line would have been to the left. And if it were to the left, then I know that the curve would have to go this way, with the back of the curve towards the directrix line, hugging the focus point, the focus of all that affection. So now what we have is we've compared these 2 signs. They came out positive, so we know which way it goes. Now, the best way to do these is just to do a lot of examples. The more you do, the better at it you're going to get. So the first one I kind of worked through a little bit. It's a parabola. But then after that, we'll work a whole bunch of them where I haven't worked it out for you in advance. So we're looking at this equation right here, and I did copy off the equations that can be used for conic sections, non-circles, in the polar coordinate system. This is for your parabola, your hyperbola, and your ellipse, all right? Either one of these two. My equation is -1 over 1 plus cosine of theta. So when I'm looking at this, step one, make sure the denominator has a +1 as the constant term at the beginning, and it does. That means the absolute value of the coefficient of the trig function is the eccentricity. That means that I must have eccentricity of 1, and that means it has to be a parabola. So I know now that it must be a parabola. All right. The next thing that I want to do is I want to figure out which way it's running. I have cosine in the equation, so that must mean that it's running either left or right, right? If it were sine, it would be running up or down. But because it's cosine, it's got to be running left or right. Where would the directrix line be then? Well, to determine where the directrix line is, I need to find the focal parameter. Now, my numerator is a -1, and because it's a -1, I can use that and the fact that the eccentricity is +1 to determine that the focal parameter is a -1. That doesn't mean it's to the left. You have to take the sign of the focal parameter in conjunction with the sign in the middle. Or you can simply start from when you have a +1 here, compare these two signs. If they're different, then it will be on the negative side. If they're the same, it will be on the positive side. These are different, so I know it's going to be on the negative side. Cosine is going to be left or right of the pole, and because it's negative, it's got to be to the left of the pole. So now I know that the vertex has to be somewhere between the focus and the directrix. The focus point for the parabola is located at the pole. The directrix is going to be to the left of the pole running vertically. Again, cosine is going to cause the parabola to open to the right or to open to the left, right? If it were sine, it would open up or it would open down. So what I have so far in my image, if I draw it out here, is I have the focus located here at the pole. It's cosine, so I know that it is opening either left or right. The directrix is to the left of the pole because the combination of signs was negative, and this is the directrix. Now, based on our knowledge of parabolas, where is the vertex? The vertex is the center of the parabola. The vertex is going to be exactly halfway between the focus and the directrix line. Not only that, but I know exactly where this line is going to be because my focal parameter was -1, which means the distance between the focus point and the directrix line is 1. The distance has to be positive. Because it's to the left, this directrix line has to actually be x equal -1. Now I'm ready to find where the center of it is, but I know the center is going to have to be somewhere halfway in between. It's going to have to be between the directrix and the focus. And it has to hug the focus, which tells me it's going to be on the polar axis. Well, actually to the left of the polar axis on the negative x-axis, halfway in between. So then I can locate the vertex right there, halfway in between. Now I could give you the coordinates immediately in the rectangular system because it's halfway between the origin and the line -1. It's got to be at -1/2, 0. That will not, however, give you the coordinates in the polar system. In the polar system, it is in the direction of pi and at a value of 1/2 away from the pole. So in the polar system, it would be 1/2, pi. So both of those names would give us that point, one in each system. So the vertex in the rectangular system would be at -1/2, 0. And in the polar system, it would be at 1/2 pi, right? In the pi direction, 1/2. Now, the next thing that we want to do, of course, is we want to be able to graph the rest of the parabola. And when we're looking at graphing the rest of the parabola, we need to think about the endpoints of the lattice rectum. That's what's going to give us our other 2 points so we can actually draw the parabola. So where is the lattice rectum? Well, remember the distance from one endpoint of the lattice rectum to the focus is the same as the focal parameter. So it's got to be a distance of 1 above the focus. So up here at a distance of 1 is going to be one endpoint of the lattice rectum, and a distance of 1 below is the other one. Now, this, of course, also has two names, and it depends on your professor as to which one they want. So we have the endpoints of the lattice rectum. In the rectangular system, this would be at 1 or 0, 1. And in the polar system, it would be at 1 pi over 2. And this down here would be at 0, -1 in the rectangular system. And in the polar system, it would be at 1, 3 pi over 2. Oops, I wrote rectangular. Polar. Right? Now we can take a look at what we've got on the parabola so far. We know that we have the center at -0.50. That is in the rectangular system. And this is the line x equal -1. And then we've got the endpoints of the lattice rectum. And the lattice rectum is graphed here in purple. Now, it does help to actually graph other points instead of just having these 3, because they might be relatively close together. It doesn't really give you a great feel. For something like that, you want to choose something further out. Now, let's see what happens if I choose something, say, right here over this pi over 3 line. Now, we want to write the equation of our polar conic section again. So we have r equal -1 over 1 plus cosine of theta. We have r equal -1, 1 plus cosine of theta. Now, here's the weird thing that you have to remember about the polar coordinate system. That negative in the top is very likely going to make the radius negative, which is going to make it graph in the opposite quadrant. So if I want it to graph at pi over 3, I might have to choose the one that's at 4 pi over 3 to get it to shoot out the other end. Pi over 3, the cosine is 1/2. 1 plus 1/2 is 3/2. And that would give me -2/3. But the negative radius value makes it come out along this 4 pi over 3 line at a distance of -2/3, which is right where it is. So if I wanted to graph in that direction, take something along the 180-degree line along 4 pi over 3, and let's see what happens there. So we're going to compute r of 4 pi over 3, which gives me -1 over 1 plus the cosine of 4 pi over 3. Now, 4 pi over 3 is going to give me a -1/2, right? Because I'm in quadrant 3. So this is going to give me -1 over 1 minus 1/2, which is -1 over 1/2, which is a -2. That means it's actually going to graph in the opposite quadrant, quadrant 1, on the second radial circle along the pi over 3, 4 pi over 3 line. And that would give us this point right there, right? And that will enable us to draw a better one. And then I would do the same thing for something down here. I would also use a multiple of pi over 3, because I know the cosine of pi over 3 is 1/2, and then I don't have to get into the radicals, and it makes it easier to compute exactly where it is. So because I want it to come out down here, and because of the -1 in the numerator, I know that it's probably going to come up negative. And so I'm going to choose, instead of using this one along 5 pi over 3, I'm going to choose the one out here in quadrant 2, 2 pi over 3. So that would also be a negative 1/2. It's going to give me the same value. It's going to give me a negative 2. So it's actually going to plot in quadrant 4 along the 2 pi over 3, 5 pi over 3 line at a distance of 2. And that way I can get a better graph. Let's take a look at the next example. In this example, we have 3 divided by negative 4 plus 3 sine of theta. Definitely not in working form, so I can't tell yet what kind of conic section it's going to be. I can't tell if it's a parabola or an ellipse or hyperbola. First, I have to make that negative 4 turn into a 1 by dividing numerator and denominator by negative 4. So I'm going to multiply the numerator by 1 over negative 4 and the denominator by 1 over negative 4. This is going to give me r equals negative 3 over 4 times positive 1 minus 3 over 4 sine of theta. It changes the product of the eccentricity and the focal parameter, and it changes the coefficient of the trig function. Now, when I look at it, I take the absolute value of the coefficient of the trig function, and that's going to represent the eccentricity. So my eccentricity is equal to 3/4. Because that's less than 1, I know I have an ellipse. All right? Then I take the numerator, which is eccentricity times the focal parameter, distance from the focus point to the directrix line, and I set that equal to what I have on top. So I have eccentricity times d equal to negative 3/4. I know the eccentricity is 3/4. So I have 3/4 times d equal negative 3/4. So d must equal a negative 1. So the distance from the focus point to the directrix line closest to it is 1. Now, I want to take a look in the working form at the combination of these two signs. It's a negative in the numerator and a negative in the middle in the denominator. Multiplied together gives me a positive. So the directrix is on the positive side, either to the right for cosine or above for sine. I have sine, so it's above. So I have an ellipse. Now, which way is it running? Well, I have sine, which means it has to be running vertically, which means the directrix line has to be horizontal. So what I know so far is that it's got to be running something like this, and I've got a focus point and I've got directrices somewhere like this, and one of the focus points has to be at the pole, but I don't know which one. So how am I going to figure out the next bit of information? What we have so far is we know we have a focus right there at the pole. I know the distance from that to a directrix line is 1. Now, unfortunately, that's going to be super, super close. But basically, the distance between that and the closest directrix line is 1. All right, so we've got something right there. Now, what do I need? Well, I need to know what the endpoints of the major axis are. So I need to locate the major axis. I said because it's sine, it's got to be running vertically. If it's running vertically, then what I'm looking for are the endpoints at the top and the bottom. But because the focus is at the pole and it's running vertically, both focus lines end up on this pi over 2, 3 pi over 2 line, which means that the vertices also have to be on that pi over 2, 3 pi over 2 line. So what we do is we substitute pi over 2 and 3 pi over 2 into the equation in either the original or working form to find the radius at the angles pi over 2 and 3 pi over 2. And again, that's because we know it's running vertically. So now coming up here, I'm going to find r of pi over 2, which I can write as, well, we can go back to the original if you want. 3 over -4 plus 3 times the sine of pi over 2. Now the sine of pi over 2 is 1, so this becomes 3 over -1, which is -3. Now where is that going to graph? That's the ordered pair -3 pi over 2. Because the radius is negative, it's actually going to plot down along the 3 pi over 2 line. And the distance is 3, so we come out 1, 2, 3 on the third radial circle, and we plot that point. And the coordinates of that point are -3 pi over 2. And that's in the polar coordinate system. Now I've got that one. Where's the other one? Well, the other one comes from plugging in 3 pi over 2. So now I want to go back and I want to plug in 3 pi over 2. So I get the same relationship, 3 divided by -4 plus 3 sine, but this time of 3 pi over 2. The sine of 3 pi over 2 is a -1, so I get 3 over -7, which tells me that it's very, very close to the focus. It's not even out there at 1 along the radial circle. I wish I could make this a lot bigger. This one's really small. It's close to a half, but a little bit less. Now, it's a negative, so it's going to shoot out in 180 degree, the opposite direction. So 3 pi over 2 is straight down, but because it's a negative radius, it's going to graph straight up at a distance of almost a half. So that would be right about here. So our F for the focus is actually pretty large, and it's actually bleeding over into where our other vertex is. Now, we've got the 2 vertices on here. Where would the center be? Well, the center has to be halfway in between. So I've got this up at a distance of 3/7 and this down at a distance of 3. So let's add those 2 numbers together and locate what's halfway in between. So we're trying to locate the center. So we're going to take 3/7 up plus 3 down. 3 down, this of course could be written as 21 over 7. So this gives me 24 over 7. Now that's the total distance from this vertice to this vertice. And what I want to do is I want to find half of it, because half that distance is how far it is from the center to each vertex point. So half of that distance is going to be equal to 12 over 7. Now 12 over 7 is a little bit more than 1. It's not quite up to, or it's maybe 1.5. I'm not sure. Let's see what it says. 12 divided by 7 is 1.7. So it's roughly 1.7. Now, that's not at a distance of 1.7 from the pole. It's at a distance of 1.7 from each vertice. All right. So I need to take one of the vertices and I need to find what is 12/7 away from it. So I'm going to take the upper one and I'm going to subtract that value because I know it's got to be below it. So 3/7 minus 12/7 gives me a -9/7. So the center is at -9/7. And 9/7 is about 1.3. So right about here is the center. And the center is going to be located, you can write it different ways, but one way to write it is 9/7 3 pi over 2, because it is down in the negative direction down here, 3 pi over 2. That's where the center is. I have the 2 vertices, I have the center. I have one directrix line. I need to find the other directrix line, and I need to find the other focus point. I know that the focus here is at the pole, and this one is down here at -9/7. So the distance from the center to the focus is 9/7. So another 9/7 below the center, I should have the other focus. So locate the other foci. And that's going to be at 9/7 plus another 9/7, which would be 18/7, which is going to be about 2.5, which fits with what it looks like up above. It's very close to the vertex at the bottom. So we now have this one. And we can write the coordinates of that vertex as well. It's getting a little crowded on there. So I'll say that this is at 18/7 3 pi over 2. And that's in the polar system. And we could also write it in the rectangular system as 0, negative 18/7. Now, the next thing we need, of course, are the two sides, and we need the other directrix. So we need the minor vertices so that we can actually draw the ellipse, and we need to locate the other directrix. Now, we know the directrix, we know the focal parameter distance was A1, I believe. Let's go back up and look. Yes, the distance from the focus to the directrix is 1. So this focus is at 18/7. So the other directrix needs to be at 25/7. So now we can locate the other directrix. And we know it's got to be a distance of 1 away. So it's going to be 18/7 plus 7/7, which is equal to 25/7. And it is, of course, a horizontal line. So it's going to be y equal 25/7, which turns out to be about 3.6, a little bit less. So we've got another directrix line at 1, 2, 3, about here. So this is our other directrix line. Now we need to find the sides. Now, unfortunately, the sides are not going to be at 0 and pi because that would be up here, and the center is down here at 9/7 3 pi over 2. And it's got to be even with that, all right? So in order to find them in the polar coordinate system, it would be very difficult. I'd have to figure out what puts me down here even with this, what angles that would be. The easier thing to do is to go back to the rectangular system and to use what you know about A and C to locate B. So this time we don't have A and B and find C. We have A and C, we find B. So what we've discovered up here is the distance from the center to the edge turned out to be 12/7. So this up here was A. And the focus point had to be a distance of 9/7. So this focus point, C, is 9/7. And now what we want to do is we want to find the value of B. So we can come down here and we have in an ellipse, B squared equals A squared minus C squared. So we don't know B squared. We know A squared is 12/7 squared, and C squared is 9/7 squared. Now, when we add those together, they have the same denominator, so it's going to be 49. We have 144 minus 81, which turns out to be 63, I believe. Yes, 63. So coming down here, we have B squared equals 63/49. So B is going to be over 7, and it's going to be 3 square roots of 7, which of course can also be written as 3 over the square root of 7. Now, how big is that? Well, let's calculate that. It's about 1.13, all right? So we have roughly 1.13, all right? So very close to 1. Coming up to the center then, we move to the right and to the left one, and this time we need the rectangular system behind the polar system in order to figure that out. So it's a little bit over here. So it's going to be roughly right here, even with the center, and right here. And finally, we can draw our ellipse. rather small. All right. So hopefully this makes sense to you. You can see sort of how to graph it. This one was very small, so it's hard to see all the detail, but this is basically how we're going to graph them. Let's take a look now at another one. Oh, here it is blown up a little bit bigger. This will make it make a little bit more sense. So in the rectangular system, we found where the center was, and then we moved to the left and the right. So this is -3 to the square root of 7, -9/7. Remember, it was at 9/7, 3 pi over 2 for the center. So this is at -9/7, and this is -3 over the square root of 7. That's what we found B to be. And then 3 over the square root of 7 to the right. And then we can see we've got these graphed in the polar system. So we've got these two right here. And then we've got the focus at the pole and the focus down here. All right. And we've got our two directrix lines at -25/7 and at 1. Let's take a look at our next one. This one is almost identical to the one we just did, but instead of sine, it has cosine. So instead of running vertically, whatever it is, it's going to run horizontally. So again, we start by making the leading coefficient there in the denominator a +1. So this gives us R equals -3/4 over 1 minus 3/4 cosine of theta. Again, the eccentricity is 3/4, so it is going to be an ellipse because it's less than 1. And we know the eccentricity times the focal parameter is equal to -3/4, which means that the focal parameter itself is -1. The combination of these two signs in working form is positive, so we know it's on the positive side of the pole. So because it's cosine, it's got to be left or right, and the positive side is the right. So the directrix is going to be at the right. The ellipse is going to be running horizontally like this, and we're going to have a directrix running vertically on the right side of the pole. So that means that basically, if I envision this ellipse, this is the focus at the pole, and here's the directrix to the right of it, right? So it's got to be running in this direction, okay? It has to be something like this. If it were more on the right side, then the directrix would be on the left, right? So we've got to have some kind of picture like this. We want to figure out where's the center, where are the end points, and where are the minor vertices. Now, notice that if we have this, the major vertices have to be along the 0 and pi line. So when we have cosine in there, we can find the major vertices by plugging in the values of 0 and pi into the equation for the particular conic section. So let's go ahead and plug in those values and find the end points of the major vertices. So when we're looking at one of them, I'm going to say, okay, R of 0 radians is equal to 3/-4 plus 3 cosine of 0. The cosine of 0 is 1, so I get -4 plus 3, which is a -1, so I get -3. That means that it's actually plotting 180 degrees opposite, coming out in the pi direction. So it's got to be that this one over here is the point -3, 0 radians, right? And in the rectangular system, it would also be -3, 0, which that doesn't always happen, but it would be the same. Now, how do I get the other endpoint of the major vertice? Well, the other one has to be along the pi line, but it's probably going to give me a negative radius, so it's going to shoot out the other direction. So now I'm going to try R of pi radians, which gives me 3/-4 plus 3 times the cosine of pi. Now the cosine of pi is -1, so that gives me 3/-7, which gives me -3/7. So again, that's going to be the ordered pair that's at this endpoint. That's going to be the ordered pair -3/7 pi radians. right? And that's in the polar coordinate system. It graphs in the 0 direction because the radius was negative. Remember, that shoots it out on that 180-degree line. The equation for the directrix over here, it's 1 away from the pole, so that's got to be x equal 1. Let's take the information we've gathered so far and let's go ahead and put it out here onto our graph. So I have a focus at the pole, and I have, what else do I have? I have -3/7 to the right, which is going to be really close in. So about here. And then I have -3 in the 0 direction, which would be here. All right. And I know that the directrix line, which I'll graph in blue, is x equal 1. Now, again, we've already done this particular ellipse in the vertical direction. Now we're doing the horizontal. We need to know where the center is. It's got to be halfway between the black dots, the 2 vertices. So again, we take 3/7 plus 3. We add it together. We got 24/7, and half of that was 12/7. So we're going to take the 3/7 and we want to subtract 12/7, which puts us at -9/7. So our center has to be out here at -9/7. So somewhere around in here. So the center can be located in the polar coordinate system at 9/7 pi, that's polar, or -9/7 0 in the rectangular system, whichever way you want to write it. Now, we want to know where the other focus point is, so we need to know C, but the distance between these two is 9/7. So C is equal to 9/7. So I can take 9/7 and add it to the center, and that will put me out here at 18/7. And that's got to be where the other focal point is. Right? So the other focus point has to be at the location 18/7 in the pi direction for polar, or you can write it as -18/7 0 in the rectangular system, depending on what your professor wants. Now we need the minor vertices, so we do the same thing we did previously. We find the value of B by computing A and C. A is the distance from the center to the edge, which we found to be 12/7. So up here. And then we take a squared minus c squared, take the square root, which gives us 3 over the square root of 7, which I believe we said 3 over the square root of 7 is about 1.13. So that would be up from the center 1.13, which is about here, and down 1.13 is about there. And then we do our best to make it look like an ellipse. All right, so it is a relatively, I mean, it's not terribly oblong. It's not too circular, but it's not terribly oblong. We could actually look at the eccentricity value. The eccentricity value that we got was 3/4, which is more towards the elliptical and less of the circular side. So it's got to be relatively long. All right. Oh, we didn't put the other directrix line on. So the other directrix line is going to be a distance of 1 away from this focus. This focus is at 18/7, so that's going to be at 25/7 right on the other side, which is going to be about here. All right, so this is going to be x equal -25/7, and this is x equal 1. All right, so we have the equations of the two directrices lines. Those have to be written in rectangular system, although you could replace x with r cosine of theta. So you could write r cosine theta equals -25/7 or 1. So hopefully this is starting to make sense to you. We've not done a hyperbole yet. So let's take a look at another example. I did go ahead and graph these for you. So if you want to see what they look like, this is what this one looks like if you pull it in relatively close. So I've got the two focus points here. I've got the two directrix lines dashed in blue, and I've got the center marked here with an X. I've got the two minor vertices, and then I've got the two major vertices in the polar coordinate system. The minor vertices need to be in the rectangular system because we don't know what angle it is that produces those. Now, could we find the angle? Yes. Tangent of theta is y over x. And so we could take these values and compute the angle by using arctangent. All right, let's take a look now at our next example. This is example 4. We have 5 divided by -1 plus 2 sine of theta. It is a 1, but it's a -1, and that is not allowed. So we're going to multiply numerator and denominator by -1. And -1 divided by itself is, of course, still 1. So now we have the equation r equals -5 divided by 1 minus 2 sine theta. All right, so whatever it is, it's running vertically. So it's either an ellipse running vertically, or it's a hyperbola that opens up and down, or it's a parabola that opens up or down. All right, so it's running vertically. And that's because we have sine. Now, once I have the 1 here, I want to locate the eccentricity, which is the absolute value of the coefficient. So my eccentricity is equal to 2. Now that I have eccentricity of 2, that's greater than 1. So I know that I have a hyperbola. So this is our first hyperbola. Okay, so when I'm looking at that, the next thing I want to find is the focal parameter, and that's going to be the new numerator, which is -5. I know the eccentricity is 2, so 2d equals -5, or d is equal to -5/2, which means the distance from the focus to the directrix line closest to it is 5/2. Now, we take the combination of these two signs, which is going to be positive, and that tells us that the directrix line is located above. Sine is either going to be above or below. Cosine is left or right. So because these are both negative, the combination is positive, and it's going to be above. So we have a focus at the pole, we have a hyperbola, and we have a directrix line above it. So let's think about what that has to look like. So coming down here, we're going to put our focus at the pole. We have a directrix line which has to be above a distance of 5/2. So that would be 2.5, 2.5, which would be right here. And we know it has to open up and down like that. So this way and this way, which means that the directrix lines have to run horizontally. So this is going to be right here in between 2 and 3. And this, of course, is the equation y equal 5/2, or if you want it in the polar system, replace y with r sine theta equal 5/2. All right, so this is one directrix line that we have right there. Okay, now remember the way that they look. The hyperbola has two curved sections, and the curved sections hug the focus point. So one of them's got to hug this and turn its back to the directrix line. So one of them's got to come up like this and come down like that. But we know that the directrix lines are on either side of the center. So the center's got to be above. So this has to be the lower half of a hyperbola opening up and down. Now we want to locate where those places of the major vertices are. Since it opens up and down, they've got to be along the pi/2, 3pi/2 line. So we're going to come up here and we're going to compute the value of r of pi over 2 and r of 3 pi over 2. So this is going to give me 5 over negative 1 plus 2 sine of pi over 2, which is 1. So I get negative 1 plus 2, which is 1. This gives me 5. So this is the ordered pair 5 comma pi over 2 in the polar system, which means it graphs directly up, and that's going to be right here. So my vertices, and you might make a list out to the side because it gets kind of crowded in there, is 5 pi over 2. That's one of them. Where's the other one? It's got to be at 3 pi over 2. So I plug that in. I get 5 over negative 1 plus 2 sine of 3 pi over 2. And you can plug it into working form or the original. It doesn't matter. And this gives me 5 over negative 3. All right. The sine of 3 pi over 2 is negative. So negative 1 minus 2 is negative 3. So I have 5 thirds. It's negative. Now, because it's negative, it's not going to graph below the pole. It's actually going to shoot out in the opposite direction at a distance of 5 thirds above the pole. So this would be 1 and 2 thirds. So that would be here. So this would be negative 5 thirds, 3 pi over 2, right? Now, we need to figure out where the center is. The center has to be halfway between the two vertices. Now, this is at a distance of 5, and this is at a distance of 5 thirds. So I need to know what 5 minus 5 thirds is, because that's how far it is between them. So that would be the transverse axis length. So transverse axis is equal to 5 minus 5 thirds. 5 is 15 thirds. So this gives us 10 thirds long. So the center, or rather the value of A from the center to one vertex is going to be half that, which is going to be 5 thirds. So if I go from 5 thirds to 5 up 5 thirds, that's going to be at 10 thirds. So the center is going to be at 10 thirds pi over 2, right? Or you could write it as 0 10 thirds in the rectangular system. 10 thirds is going to be 3 and a third. So 1, let me change colors. 1, 2, 3 and a third. So it's right about here. All right, X marks the center. Okay, so we've got the center here. We've got the two major vertices. I know what A is. I can also locate C. C is between the center and the focus point, and the center is up here at 10 thirds, so C is 10 thirds. So now I've located the value of C, which is 10 thirds, right? Now I want to go ahead and find where the other focus point is. It's got to be 10 thirds on the other side of the center. So 10 thirds plus another 10 thirds would be 20 thirds, which is almost at 7. So the other focal point has to be up here, 5, 6, 7. So it's got to be right there. Right? Now, where is the other directrix line? Well, we can do the directrix line many, many different ways. We know that from the focus to the directrix line was 5 thirds. 5 halves rather. So we have from here to here is 5 halves. So I could take the 20 thirds minus 5 halves and locate the other one. I can also take the distance between the center and the directrix line to locate the other directrix line. However you want to do it, it needs to be equidistant from the center, but on the other side of the center. So I'm going to use the center. So the line is at 5 halves, and this is at 10 thirds. So the distance between the two for the other directrix line is going to be 10 thirds minus 5 halves, which I need to rewrite them both as 6. So that becomes 20 over 6 minus 15 over 6, which is 5 over 6. So 5/6 plus 10/3, basically. So that would be 25/6, which is just over 4. So just barely above 1, 2, 3, 4. Barely above that line right there. Right? And we said that would be at y equals 25/6. I believe that's what we said. All right, so this becomes y equal 25/6. Okay, all right, now we still don't have the graph drawn, right? What we have is we have the vertices and we have the other part. We need to have the minor vertices so we can draw the rest of it. We need that box. So we're going to locate the minor vertices coming out from the center. And remember, we're going to find the minor vertice by using the values of A and C. But for a hyperbola, C is longer than A, so it becomes C squared minus A squared. So we're going to locate B squared by computing C squared minus A squared. Now, A squared is going to be 5/3 squared. And, oh, I put A first, my bad. C is 10/3 squared minus 5/3 squared for A squared. All right, and that's going to give us 100/9 minus 25/9, which is 75/9. So the value of B is going to be the square root of 75, which is 5 square roots of 3 divided by 3, which is the same as 5 over the square root of 3. Now, we can figure out what that is approximately. 5 divided by the square root of 3, which turns out to be about 2.9, a little bit less. It's actually 2.88675. So it's very close to 2.9. That's as close as we're going to get. All right, you can't even tell the difference between 2.9 and 2.8. So moving from the center to the left and to the right, a distance of 2.8 on the rectangular system. So I'm going to graph these in gray. So moving to the right, 1, 2.9, so about here. And I'm going to make it an X. And then moving to the left, 1, 2.9, make it an X. Now we need to draw a box. All right, so we've got the major vertices, we've got the minor vertices. Our box needs to connect each of the minor vertices and the major vertices in the sides of the box. So I'm going to go straight down until I reach the height of the other one. And maybe we need another color. We'll do the box in pink so it shows up. So I'm coming straight across from 5. And then I'm going straight down through this one until I reach the center of the other vertex. Straight across and then straight down. There's my box. Now you're going to want to take a straight edge. I use an index card, but you can also use a credit card or something like that. You want to connect the corners of the box and you want to draw a straight line, make it dashed, that goes through the corners of that box. And then we want to do the same on the other diagonal. And I generally only draw them on the outside of the box because it's really where it affects things. All right, so we've got our 2 diagonals. We're finally ready to actually draw the hyperbola. We don't have the hyperbola on here. The only thing that's on the hyperbola that's on this mess so far are the 2 blue dots, the 2 vertices. So now we want to go ahead and draw the rest of it by graphing along the asymptote lines. And it was signed, so it opens up and down. Right? And now you can see that you've got the hyperbola here. It's a little bit difficult to see everything on the handwritten one, so I have produced for you guys ones on Desmos. So if you want to copy off that link and then you want to open it up, if you're at home watching on the video, here is the one that we have right here. So we've got our two lines at 25/6 and 5/2. We've got our foci out here at, this is in the rectangular system, looks like, and the foci at 0, 0. And then we've got our vertices in the polar system that you've got out here. Okay. All right. Let's take a look at another example. Let's take a look now at this particular one. We have 3/2 minus sine theta. What I'd like you to do is pause the video, do all of the work, and then turn the video back on, and we'll compare our answers. Go ahead and pause the video now. So first thing to do is to divide numerator and denominator by 2. That gives us this form of the equation right here. That means the eccentricity is 3, so it is a hyperbola. The eccentricity times the focal parameter distance, ED, is going to be 3/2. The eccentricity is 3, so that makes the focal parameter 1/2. Now, the combination of signs here is negative, and it is sine. So that means the directrix is going to be below the pole. All right, so we've got the directrix line below the pole at a distance of 1/2 from the focus point. Now on this one, it is extremely tight and small in there. So I want to go ahead and show you what you've got right here. So our first directrix is right here, 1/2 below the focus that's at the pole. And notice, because this is below, it means that the majority of the hyperbola is below. Now we need to locate our major and minor vertices. They're going to be along this pi/2, 3pi/2 line because it's sine, so it opens up and down. So we come back over here and we plug in the pi/2 and 3pi/2 into either the original or the working form, and we get two vertices, -3/4 pi/2 and 3/8 3pi/2. Now, once we have these two, we graph them. Notice that this one is actually going to graph below the pole because the radius is negative. So coming over here to our picture again, what we see is that it's a distance of 3/4 from the pole in the negative pi/2 direction. And then we've got 3/8 3pi/2. So oddly, they kind of flip-flop, but that's just the way it works with polar coordinate systems. Once we have that, we can find the length of the transverse axis, which is the distance between the two. Now I can take the 3/4 and subtract 3/8. And when I do that, I come up with 3/8. So the entire length between the two vertices is 3/8. Now A is half of that. So it would be half of 3/8 or 3/16. So I know where the center's got to be. It's got to be halfway between those vertices. And I found that A, which is from the center to a vertex, is 3/16. So I can take 3/8 and add 3/16, which will give me the location of the center. Or I could take 3/4 and subtract 3/16, and that will also give me the location of the center. So the center over here turns out to be at 9/16 at 3pi/2. That means that it's also a distance of 9/16 from the pole, which means that C is, wait, what was I saying? Yes, C is equal to 9/16. The distance from the focus to the center is 9/16. So where's the other focus? Take this value that we have here for the center, which I believe is 9/16, and add another 9/16. So that would give us 18/16, which will give us the other focus point down here. And I'm trying to find where the other focus point is over here. Yes, 18/16 gives us -9/8 in the rectangular system. All right. Now, in order to graph it, you're going to need the covertices along the conjugate axis, the ghost ones. So you need to be able to figure out what B is. So coming back over here to your graph, we're going to take the values for A and C. A is 3/16, C is 9/16, and we're going to plug them into the formula for a hyperbola. B squared equals C squared minus A squared. And that gives us that B is roughly about 0.5. So let's come over here, and I'm actually going to take a picture of this, and I'm going to superimpose it over on the other screen as soon as I can find my snipping tool. There we go, snipping tool. There it is. Click. All right. Now I'm going to take this and I'm going to paste it over here. Right? And I'm going to blow it up a little bit so we can see a little bit larger. Right? So here's what I have so far. Now, how do I know how to draw the hyperbola? I need the box. I need the asymptote lines. You can tell this is opening up very, very widely. All right. So again, our eccentricity turned out to be 3, which is a good bit larger than 1. So it's opening very wide. Now, what I want to do here is I want to take this and I want to go from the center, the distance of B out from the center, which was a little bit more than 1/2. So a distance of 1/2 is this distance right here. So coming out about 1/2 would put me here a little bit more than that, and here a little bit more than that, right? And then I'm going to draw a box that connects the major vertices and the ghost vertices, where they're the centers of each side of the box. So there's my box. And then I'm going to take an index card and I'm going to draw the diagonals, which looks like this. So you can see the diagonals coming out here, very close, and coming out here. Right, like that. And then you can draw the other one as well. Keep in mind that it's not exact because I didn't draw it exactly. All right, and you can see that you can draw the hyperbola from that point. So hyperbolas involve a lot more work than the ellipses do, and a tremendous amount more work than the parabolas do. But I hope that this gives you an understanding of how to work out these fascinating curves and that you've enjoyed our study of the polar coordinate system. In the next set of videos, we'll be looking at some applications for different types of functions. And we'll be looking at arc length of a regular curve in the rectangular system. We'll be looking at surface area in the rectangular system, work-related problems, moments, and centers of gravity, centroids, and we may have time to do a little bit more. I hope you'll join me for the next series of videos that will complete this course.